All right, so on excuse me, Friday, we left off talking about electrophilic aromatic substitution. And let me just recap that real quick. All right, so the electrophilic part, let me, okay, hold up. Give me a second. Shrink this down so I can move that. All right, so let's kind of zoom in on that whole idea of electrophilic aromatic substitution. Excuse me. So the electrophilic part is my electrophile being added to the ring. And there is another class of substitution reactions for aromatic. That's the opposite. There's nucleophilic aromatic substitution, where the ring is acting as a nucleophile and the ring is acting as the electrophile and you're adding a nucleophile. But in this case, the electrophile is being added and the ring, the aromatic system, is acting as a nucleophile. Right. And then the substitution part is, I think I mentioned this on Friday, but I'll recap it. The substitution part is basically removal of a hydrogen and replacing it with the incoming electrophile. Right, so when you hear that phrase, electrophilic aromatic substitution, that's what we're talking about on the ring. So the ring is the nucleophile, the electrophile is external, and the substitution part is where the hydrogen gets swapped out. All right, so let's talk about now. Let's talk about one of the other reactions here, and that is the Frito alkylation. That's the second reaction. If I can cut that out. Shucks, come on, Russell. Here. Trying to cut the word out, but that's okay. All right, so so in this reaction, this Frito alkylation is exactly what you expect. You're adding, hold up. All right, so you're adding in an alkyl group to the ring. So R is an alkyl group. All right, so if you have an alkyl halide, which we know at this point because we studied alkyl halides more than once, started out talking about alkyl halides. We did alkyl halides, converting them into organometallics, and now We're using them for another purpose. So as you can probably ascertain, it's a very versatile reactant. You can do a lot of different things with alkyl halides because of that carbon halogen bond that's so easily kind of compromised, right? You can do a lot with that. So the Frito Kraft's alkylation is the addition of an alkyl group. This reaction is no different than the halogenation. The only difference is what the catalyst is and what your alkyl halide is or what your electrophile is. That's the only difference. The mechanism is identical to halogenation. All of your aromatic substitution, electrophilic aromatic substitution reactions are going to follow the same path. All right, so halogenation and Frito Kraft's alkylation follow the same path. What are the 3 steps in the mechanism? Because it might tell me that.
Preparing the
Hold up, let me turn my speaker up. Go ahead.
preparing the electrophile, the attack of the ring on electrophile, and reestablishing aromaticity.
Yes, same. So those 3 steps happen in any aromatic substitution. You have a preparation phase where your electrophile is prepared. You have a nucleophilic attack of the ring on the electrophile, and then followed by in the final step, reestablish the aromaticity. So let's look at that for this reaction right here. Right, so we'll take our electrophile. Let's just take isopropyl or 2-chloropropane. Right, so we'll take that because it's a secondary carbon. This does the substitution pattern on carbon does matter. I'm gonna show you another example where you have a primary carbon and you have a chance to stabilize it through rearrangement or something like that. It's gonna happen. All right, so we got this plus aluminum trichloride. Right. Let me put some space in here because I need to show. Put this down here. All right, so with the chlorine having lone pairs and being a Lewis base and aluminum being a Lewis acid, you're gonna get coordination between these two. Right, aluminum is a Lewis acid; it can accept a pair of electrons, so you get this coordination, right? But then that happens. This app is really tripping. My nerves too. So once that happens, you actually break the carbon chlorine bond, right? So you coordinate to the metal, and then the carbon chlorine bond breaks, and it leaves you with a carbocation. So a secondary carbocation is here, plus AlCl4 minus. So you can already see the setup. You have your electrophile now, and then on this side you have your negatively charged aluminum species that will eventually act as a base in that elimination step where you reestablish aromaticity. Right, so it'll act as a base in the final step. So that's step 1.
I have a question.
Go ahead.
What does that dash line mean?
So the dash line, that's a great question. It's more of a coordinate covalent bond than a covalent bond. So a covalent bond is the chlorine would just simply hand over all the electrons and make a bond with aluminum, right? But a coordinate covalent bond is almost similar. It's very similar to like an ionic attraction, where aluminum has empty orbitals and the chlorine has a pair of electrons that it can donate to aluminum, but it's not establishing a covalent bond right away. So it's more like a what we call like a ligand. So the chlorine is kind of attaches itself to the metal, but not in a covalent fashion. So you're not making like remember when we did organometallics, you had this covalent bond between carbon and metal. Here is more like it's what we call a coordinate covalent bond. So it's just one atom furnishing a pair of electrons and kind of mingling with the empty orbital on the metal, right?
Okay.
That's a great question. I'm not sure if y'all talked about that in general chemistry part 2, because that's where you would have seen it. Or, and I know you didn't take inorganic. You may have if you're doing like a minor in chemistry, but that's more of a metal non-metal phenomenon when you have metals that have empty orbitals and you have non-metals that have lone pairs. That happens all the time. Actually, let me go ahead. Let me make a note of that. That's an excellent question. It's a coordinate covalent bond. All right, so we've prepared our electrophile. Now in the second step, nothing new is going to happen. We're going to take the ring as the nucleophile. We're going to take the electrophile, which is this secondary carbocation, and attack it. Right, and let me make sure we understand on this ring there's a hydrogen on every carbon because all of these carbons are sp2 hybridized. Right, so there's a hydrogen on each carbon. So that's how we're able to do the elimination in the last step. So this is going to attack here, not like that. All right, and then we end up with what? What happens when I break that pi bond in the ring?
It's gonna attach to the ring.
So we're making a bond between this carbon and one of these two carbons. We're gonna pick the top one. Well, what happens to the bottom carbon? Because those hydrogens are still there, right? So I still have this here and this here, but this carbon now is deficient. So I need to put a positive charge there. Is that right?
Yeah.
Anytime I break a bond and take electrons away from an atom, I'm making that atom more positive, right? So that's going to be this is a common intermediate to aromatic substitutions, electrophilic aromatic substitution. It's a common intermediate. What's it called? Anybody? We talked about it on Friday.
Rhenium ion.
It's an rhenium ion. Good. And that's common to all electrophilic aromatic substitutions. All right, so this is step 2. All right, so the attack of the ring on the electrophile is the second step. And then in the third step, what are we doing? Something new, something groundbreaking? No, it's going to follow the exact same mechanism. Once you add that electrophile, the next step is to bring the harmony of aromaticity back to that ring. How's that going to happen?
Are you gonna have to add electrons to that positively charged carbon.
Yes, yes, we are going to have to add some electrons, but not directly, right? So we're going to do something we learned already, which is put a pi bond back here by doing an elimination, right? This iridium cation is just like if we were doing an E1 elimination and we had an alpha carbon next to it. So this carbon right here will be considered alpha. Right, so that's my alpha carbon. And then this is my carbocation. So if I pull off that alpha carbon and put a pi bond there, it's going to extinguish that plus charge. Right, so I'm going to use the aluminum as a base. It's got a negative charge. So we're just going to take this and do this. Let me fix the arrow. My arrows suck on Mondays. So we're going to do that. And then we're going to eliminate here. Eliminate that proton. And that is going to put a pi bond back in that position. My electrophile that I added is still on the ring. And then this is plus. And that hydrogen that came off is going to end up with one of the chlorines that was on the aluminum. So ACl. How do I get back to here and why? Why am I regenerating aluminum trichloride? What was it in the initial reaction? What do we use it for?
Electrophile.
It's a catalyst.
Oh.
All right. And so if it's a catalyst, it doesn't get used up. And so when I get to the end, if I'm using a catalyst in any type of reaction, at the end, the catalyst is always regenerated. I'm going to put this in all caps. That's always regenerated, always. You never, because the nature of a catalyst is that it doesn't get consumed. It's not a reactant. It's just there to facilitate the reaction by lowering the activation energy. All right, so the catalyst always gets regenerated. So anytime I'm doing one of these reactions, whatever catalyst I start with, I have to have it at the end also, right? And so with the catalyst being regenerated, it can go back and it can do it again, right? And it can go back and do it again. Somebody tell me what so how do I want to phrase this up? When we talked about the catalyst on Friday and said it gets regenerated, what do you call it when the catalyst gets spit back out after the reaction? So it's after it facilitates one reaction or one cycle and gets spit back out. What's that called? Anybody remember? Don't all answer at once now. We don't want to break the internet and break the record for the most students who answer the question all at once. Right? So anytime a catalyst is used at the beginning and the reaction goes through one cycle, we call it a turnover. Right. So anytime once you regenerate that catalyst, that's one turnover. And then it can go back and do the reaction again. That's another turnover. And I said on Friday, and I'll repeat it here because it bears repeating. Some catalysts can give you 1,000,000 turnovers. Some can give you 1,000. Some might only give you 100. It just depends on the nature of the reaction and the ability of the catalyst to facilitate that reaction. All right, let me show you another side of this reaction. Matter of fact, I'm just gonna pull the question. Where are you? Here. Let's do this question because this is an example of a Frito alkylation, but it also highlights a drawback of Frito alkylation, right? So oftentimes when you're doing Frito alkylation, you have rearrangement if you get a cation or potential cation that's not stable, right? So let's look at it. So let's take this, and this is my ring here, obviously. So this has to be my electrophile. Right. And if you look at the product, the expected product would be this, but we don't see it. How many carbons is that? 1, 2, 3. All right, we don't see that. And that's a drawback for doing Frito alkylation. There are many other reactions that you can use to couple an alkyl halide to an aromatic ring. A lot of different reactions you can use that don't involve Frito crafts. But it's there, and it was one of the first methods and first ways to do this. But there are a lot of different methods you can use for that now. But that's besides the point. We want to figure out how we got to the observed product, which is here. So let's go through the mechanism. What's the first step that's going to happen?
There's the electrophile.
We're going to prepare the electrophile by using the catalyst. All right, so we're going to take that electrophile. All right, we're going to react it in the presence of, I keep doing that, iron 3 bromide. What's going to happen? We got bromine over here with a bunch of lone pairs around it. We got a metal like iron that has empty, in this case, empty d orbitals that you can talk to that can overlap with that bromine. What's going to happen?
Coordinate covalent bond.
You're going to make a coordinate covalent bond between them. All right, so it's going to be a bond here between these two. Now you can see right away what this is setting up for. When I pull off that bromine, which is going to be extremely slow because the cation that you're making is horrible. Right? When I do this, what am I left with? I'm left with this. Make sure I got enough carbons. Yep. And this is a CH2, and that's positive, which is horrific, plus Fe. Iron tetrabromide, and that's negative. Right? We got a problem. Right? Can you see the problem? And can you tell me how we can fix it? What's the problem with the cation? Let's tackle that first. And this is something that we should be familiar with. We've seen this before. We should know at this point in our matriculation through organic what the stability trend is for a carbocation. We should know if it's primary, secondary, tertiary, or methyl, whatever. We should know that. This should be something that's readily accessible in our memory banks at this point.
Yeah, it's not stable because it's on a primary.
It's a primary carbocation, so it's horrible, right? So this is a primary right? That's bad because that's one of your more unstable carbocations. That's why I said the preparation step would be very slow because forming that cation takes a lot of energy because of its instability. How do we fix something like that? What can we do? This is also something that we've seen before. You got a primary carbocation and you got a branched carbon nearby, right? There's two things that we talked about that could be used to fix something like this.
Is it resonance?
Well, not in this case. If it was resonance, you need some electrons, but you're close. If that was a pi bond close by or a lone pair, then yes, we could do resonance and put the plus charge somewhere else. But in this case, we have this hydrogen right here that's close by. We got these hydrogens down here that are close by, right? But if I move these, I'm only going to go from a primary to a secondary. If I use this one, I can do a hydride shift, which is a type of rearrangement. Right? We've seen that before. We saw it when we were doing SN1 and E1, how sometimes if you have an unstable proton, you can rearrange the proton to get something that's more stable. Right? So if I do a hydride shift, what am I doing? How do I show that mechanistically? Anybody? What is first of all, we got to know what a hydride is. So what is a hydride? Because we can't do the shift if we don't understand if we don't know the terminology. So what's a hydride?
It's a hydrogen atom with a negative charge on
Excellent. Hydrogen atom with a pair of electrons and a negative charge. So a hydride looks like this. I like to call it like a hydrogen with muscles. All right. So in this case, we're going to take that hydrogen and the bond and the electrons in the bond and shift the whole thing over to where that carbon is. So we're going to take this whole thing and shift it over to here. All right. The electrons and the hydrogen go in a hydride shift. And that in turn is going to give me a new carbocation. This is now going to become CH3. Right, and the plus charge is now going to be here. Are y'all following that? And the only reason this happens is because I started out with a very unstable carbocation. That primary carbocation is so bad that something is gonna happen to fix that situation, right? Usually it won't happen, but the fact that it's in the presence of this catalyst and all this stuff, it happens, right? Very slowly, but it happens. So then when we move that hydride over, that's a way of stabilizing that cation. So now we got a tertiary cation. Right? And that is what the ring is going to attack. So that's why we see this product. Can y'all see it forming now or coming into view? So let's look at the next step. Next step is attack of the ring. Right, so it's attacking the ring on that carbocation. So I'm going to have my ring here. Carbocation here. Anything going to change here? Anything new happening?
No.
Any rocket science going on? No. Same exact mechanism. The ring is going to attack. You get this iridium ion intermediate. Sorry about that. Let me move this over some. Plus charges here. Same exact mechanism. Well, mechanistic pathway. Got a proton, a hydrogen here that we're gonna rip off in the final step, which is to do what?
Reestablish. Yeah.
We establish aromaticity. Nothing changes. It's 3 steps. There are 3 steps to each one of these reactions. Make the electrophile, attack it with the ring, get the ring back to its original state. All right, so I'm gonna go here. What am I using as my base?
FeBr4.
The iron tetrabromide that I made in the prep step. So that's exactly right. This is negative. Excuse me. That's negative. And then I'm just going to attack here and eliminate. Right? That's simple. I'm saying simple. I don't mean to oversimplify it, but that's what happens. And it happens in every single one of these cases where the final step, whatever your catalyst is, at some of these reactions, you might actually even add a base to facilitate that step. But for the scope of this class, we're going to stick with what we have here, which is the catalyst that started out. It picked up a halogen or some other group and became negative. And now that negatively charged catalyst is going to, what a negatively charged metal with its coordinating groups. One of those groups is going to donate a pair of electrons and pull off this proton. All right, so we're going to end up with our product, which is this. Plus what? What are my 2 side products? Well, one of them is not actually a product, but what's the result of this step?
Catalyst.
We're going to regenerate the catalyst plus what?
HBr.
Plus HBr. Good. All right. So the alkylation, halogenation, and then we're going to do one more example, which is the acylation. We'll look at that next, and they're all going to follow the same mechanism, right? As a matter of fact, I'm going to get you started on the acylation, but I'm going to let you finish it. I'm not going to break y'all out though, because that's like that'll turn into nap time. We ain't doing that. So we're going to do it here. If I can cut this. Let's see if I can make that look a little bit more decent. Let's see. All right, that's better. All right, so the alkylation is different electrophile added to the ring, but the same process. This is when I'm adding in a carbonyl, especially if that R group is an alkyl group, then we just call this, hold up, that pen is way too thick. We just call this an acyl group. So what I'm adding in this case is a carbonyl. So this is actually this. Right? Notice the functional group. It's not gonna cover it over. That's all right. More than one way to skin a cat. This is the functional group that we start with for Frito Kraft's acylation. Can somebody tell me what that functional group is from part one? Anybody? Right, it's an acid chloride. I think I'm gonna say this. Don't take this the wrong way. I'm just gonna say it, but this is one of the biggest impediments to organic, period, for anybody, is knowing your functional groups, knowing how to do resonance. That's the other one, and then also understanding like different trends, like carbocations, carbanions, and arrow pushing. Don't forget about the arrow pushing. So knowing what a nucleophile is, what an electrophile is, those four things trip students up all the time. So my suggestion, and I'm suggesting this in the most loving way possible, familiarize yourself with your functional groups, because this is not the last time you're going to see this, especially if you're getting ready to take a professional exam or something like that. They're not going to point out what the functional groups are to you on a professional exam. You're going to be expected to know that. So those flashcards that you made in part one, if you made them, review them. If you didn't make them, make some, because this is a huge impediment going forward. You can't get to the meat if you can't get past the appetizer. And this is an appetizer type question, asking about functional groups. All right, so that's an acid chloride. That's what I use when I want to do Frito Kraft's acylation. All right. So the first step is, and actually I'm gonna use a real one in this case. I'm not gonna use an R group. First step is preparation of my electrophile. All right. So this is let's just use acetyl chloride. You got this chlorine again, and you notice these halogens play a significant role in these reactions, right? The halogens are very important for this type of reaction, the Frito Kraft type reaction, because they take advantage of the coordinate covalent bond between a halogen and a metal that has some empty orbitals on it. All right, so this is first step. We already know this. Right, you have a coordinate covalent bond, and then that's followed by, what? So once that chlorine associates with aluminum, what's going to happen next?
It's gonna leave a carbocation on the carbon.
So you're going to break the carbon chlorine bond. Good, excellent. And you're going to end up with that plus AlCl4. Right, and this is going to be negative. Formal charge on that salt, that aluminum is going to be negative. All right. So what happens now, and this actually, you can think about this in terms of resonance, right? It's a one of those type of two atom resonance units. Normally, we used to seeing resonance on allylic type systems, whether it's an allylic anion or cation or allylic radical. But here, it's kind of like one of those two atom units. So we could also think about this being drawn this way with a plus charge on oxygen, like that, right? That is a valid resonance form for that molecule or for that cation. All right, somebody help me out with the second step. What's going to happen?
Attack of the ring on the electrophile.
Show me how it happens if you're able to do it on, not able as in know how to do it, but if you can annotate the screen. I know you know how to do it. I have confidence in you.
Y'all draw this wrong.
It doesn't matter. Remember those pi bonds are in resonance, so you can draw it either way. Let me see what we have up top. Don't move anything. Hold up, because that's gonna move past your stuff. No, you did it right. And you can start with either one of those cations. I mean, it doesn't matter. But realize that it's the carbon that's going to be attacked, not the oxygen. So if you start with the second one, even though the oxygen has a plus charge, it's not electrophilic. It's the carbon that's the electrophile. Sound like you're making a beat over there. That's good. All right, I got you. So which ring, which pi bond are you going to use to attack that? Does it matter which one you use?
What should we use? Use this one.
Good. All right, go ahead. That's fine. All right. Yep, that's good. Excellent work so far.
No.
No, just leave it. All right. So that's that. Where are you going to put the carbonyl, the acyl group? Which so it's not going to be on the carbon with the charge on it.
Right. It's gonna be on the other
It should
one.
be on the opposite carbon.
Okay.
So you can just draw another bond from that carbon where you have that top hydrogen. You can draw a bond to the acyl group. Oh, no, not there. From the carbon where the hydrogen is.
Wait.
Hold up. Let me come in like the aircraft, like at the airport, the radar man. So we want it here, right?
Okay. Okay.
You following?
Yeah.
So that's where we want to put that. It's hard to do that, see that on this end too, because I can see it on my screen, but not on my iPad. So But that's where we are right there. Good. So can you go ahead and finish this out?
Okay.
Can somebody tell us what step 3 is going to entail? What was step 3 in every last one of these reactions that we've seen already?
So it's gonna reestablish aromaticity and the aluminum chloride is going to attack the hydrogen
Mm-hmm.
and cause another double bond to form where it was at originally.
Good, excellent. You're going to do an elimination with aluminum tetrachloride as the base. And you're going to follow that up with regenerating aluminum trichloride, put the pi bond back, reestablishing aromaticity, and that's the end of the reaction.
Oh, wait.
Good. Good.
Mm,
Good. Excellent. That's a great way to end class. Step 2, no different than any of the other reactions we've looked at. The only difference is what's participating, what type of cation you working with. The ring was basically the same. And then step 3, reestablishing aromaticity by doing an elimination, pulling off the proton adjacent to the positive charge. All right. Excellent work. This is where we're going to stop. We'll pick up on Wednesday. We're going to talk about directing effects. I think it was in the aromaticity video that I sent you already, dealing with monosubstituted rings and what happens when you react them. We're going to talk first about a little bit of nomenclature with those rings on Wednesday, and then talk about how they react. If you have a substituent on the ring, it changes the reaction outcome. It changes everything because it changes the electronics of the ring, right? It makes certain areas on the ring activated or deactivated depending on what's attached to the ring, right? So we're going to discuss that on Wednesday, and by Friday we'll be done with this, and we'll be ready to take another exam. All right, so the next exam is going to be obviously aromatics and who we do last? Addition of HX to conjugated diene. So those 2 topics. So it's gonna be a short exam, but it's gonna cover those 2 topics. All right, we'll stop here unless there are any questions. I'll see you guys back on Wednesday, God willing. Any questions about anything? Nice work to you, by the way.
Can you scroll back over to the when we were doing with iron bromide?
Yes.
It was like the one right before here.
Yeah, Tia is gonna have to clear that off the screen because otherwise it's gonna just cover up whatever I scroll back to. But I'll redraw it before I post the notes. You said the iron bromide one. You mean up top with the rearrangement? We did.
But yeah, it's the rearrangement. It's hydride shift one.
Yeah, let me go back to that. right here. Let me see if I can. There we go. All right. Any other questions about anything? All right. If you don't have a question, you can feel free to log out. I forgot to stop recording.